Hello and welcome to a new video series here on the Ludwig Fudel channel. Today we're going to talk about CUDA development, or how to accelerate your C++ application on a Nvidia GPU. Alright, before we're going to talk about CUDA, let's talk a bit about classical programming. What are the main parameters that differ from classical programming against GPU programming, or later on also CUDA programming? So first of all, on classical programming we have a linear code execution. So everything that we write is being executed linearly. So the statement that is on top comes first, and that is on bottom comes last. We have control structures like if, else, switch, case, and all that stuff. But basically we have linear execution, and it runs on the normal processor, the CPU. This is good for various work. So if we have work that needs to be adapted quite fast, so at the 1 second we are doing 3D rendering calls, on the next call we are doing audio calls, on the next function does culling, the next function executes some C# script. So basically, if you do various work, this is amazing. We have linear code execution. You do the one step linearly, then you do the next one, and it's good. But it is only suited for these various tasks. If we have a task that runs highly in parallel, so we have a bunch of data, so let's say 1000 vectors, and we want to add these 1000 vectors to another set of 1000 vectors, then this programming model comes short, because basically what we do is we do each vector separately. So we take vector A and B, we add them together, we take the next one, C and D, we add them together, and so on. So basically what we do is one addition per execution unit. So basically, or to simplify it, of course it's a bit more complicated if we take a look at the CPU, but basically what we do, at each step of our application, we are adding together two values, let's say, or two vectors. Which means if we have 1000 vectors, we need 1000 of these steps. So basically 1000 vectors do take 1000 times longer than one vector. And this is an issue, because if the data size grows, we kind of linearly go up with the execution time. And if we have many vectors to add, then we have some issues, and it's getting slow. Of course, classical programming allows us to parallelize work, because we have a CPU with multiple cores, and the average is, by taking a look at the Steam hardware survey, we have by default a 4-core CPU in average, which means that we have 8 threads available because of hyperthreading and stuff. Basically this means that we can run 8 programs simultaneously, which means that we could do, if we have 8000 vector additions that we need to do, we could run 1000 on the one thread, and at each thread basically 1000, and this would mean that we have 8 threads executing. So we have just 1000 operations to do, because we can do it in parallel with 8 threads. But we cannot really assume that this goes up quite high. We can do this, but basically the CPU is not suited for such work. It's just not designed for that. And this is where we get to GPU or CUDA programming. Basically what this means is that a simple single code is running highly parallel. So for example, a GPU is designed to do many computations simultaneously. So basically do the same operation on many values. For example, an RTX 3090 has 10,469 cores in comparison to the, let's say, 8 hyperthreading cores. There's also some hyperthreading going on, for example, on a CPU. The hyperthreading basically means that in one CPU core we can run 2 threads, and on the GPU it's a bit different. There is in one streaming multiprocessor, talking on the Nvidia side, we have 4 another execution units, and on each of these 4 execution units you have several computing units in there, and basically inside of this one of these computing units, it can do 32 threads. So basically it's a bit different than on the CPU, but if you're interested in that, I have covered this in quite some detail in my DirectX 12 series. on how this GPU actually works and how all the images that I'm showing here are built up. But basically the takeaway here is the GPU is designed to do many computations simultaneously on a simple program, and with simple I don't mean that the computation is simple. With simple I mean that it's not complicated. It doesn't have like deep branches or functions to be called, like hierarchy, switch, printing out stuff, storing stuff. So none of all these stuff, basically just the simple computation. The same computation run over like thousands of data values. So simple code running in high parallel data. So for example, code that can run parallel is, for example, culling. If we have like a camera and we want to test if every object that is in the scene is in the view plane of the camera to later on speed up rendering, for example, then we could run a culling application that runs on the GPU. If you do a very simple culling mechanism, you could basically approximate each object by a sphere, and you can also, if you have the sphere and the radius, you can also do some stuff with the camera. You can write a very uniform and simple culling algorithm which determines if an object might be inside of the camera's viewing frustum. You could write this one single thing for the GPU, for a CUDA core. You could write this, and then you can pump in massive data and go. Or for example, massive vector processing. If we have a bunch of vectors and we want to offset them, because whatever, it might be that you write an application which can scale 3D models. So basically, you take in an FBX file and you then scale each single node of this FBX file by a certain value. And you want to do this like for this new geometry which has like millions of triangles. Then you could like also easily do this on the GPU, because you have a bunch of data, but all need the same uniform processing. They all need to be scaled. So also good for the GPU. Another thing that we're gonna explore in this, we're gonna do some culling, we do some vector processing for geometry. We're gonna do everything that's kind of like explained here, we're gonna do in this tutorial series. Another example here, image processing, for example, image filtering. If you wanna like blur an image, for example, you need to do a computation, high computation method per pixel. So you need to go to each pixel and do some big computations in each pixel. And we can also run this on the GPU, so that kind of like each pixel gets its own execution thread on GPU and code runs fast. So to summarize, again, all code that operates the same but on multiple data can be used to run on a GPU. So single program, massive data. So why are we gonna use Nvidia CUDA? Well, Nvidia CUDA has many opportunities. It can be used very easily, and it has amazing debugging tools, and it is very easy to install. We're gonna get to that why it's easy to install. Basically, CUDA is just an installer that you need to run. If you're gonna do some other alternatives that I'm gonna tell you later on, you are limited, or you have like a very complicated API that you need to use to get things up and running, or you have issues with installing, but we're gonna get to that. So CUDA is very easy to use. You can easily debug this. Nvidia provides amazing debugging tools that you can do and use for your applications, and it can be easy installed and you are fast up and running. Of course, if you have such amazing opportunities, you also have some limitation. And the biggest limitation here is that CUDA natively only works on Nvidia GPUs. If this is an issue, you kind of like need to think of this. Basically, Nvidia owns, according to the Steam hardware survey, 77% approximately of the market share, which means it's quite high. And if you're designing something to run especially on CUDA, for example, CUDA is often used in data centers to run on servers. For example, Amazon AWS Cloud provides several servers that are accelerated with Nvidia GPUs, and basically if you know what environment this is running on, so basically you might do some complex hit validation for your online game on the GPU in a data center server, then you can do this, for example, on an Nvidia GPU, because you know that your data center is going to have Nvidia GPUs, and you can easily say, go for it. If you're writing portable applications, this might become an issue because of the just 77% market share. I don't know where this is like in data center stuff. I just took a look at the Steam hardware survey, and you might have some issues. Another issue, CUDA only works on Windows and Linux, or the SDK is at least only available on Windows and Linux, which I'm assuming that macOS is not working, or I didn't found the download, whatever. Basically what this means that you are only limited to Windows and Linux. By default, the most people that you are using gaming or doing some workstation work or server work run Windows or Linux. OS X is more like the, yeah, I mean, if you are like writing a creative application like Photoshop, Premiere, also video editing, photo editing software, 3D modeling, then you might also have customers that work on a Mac, on an Apple computer, because like Apple is the devices for creative people. Then you have some issues because CUDA doesn't work there, and also like Apple is a bit selective on their own GPUs. Like they had Nvidia in the past, they have AMD, they have their integrated solutions, and it is kind of like a bit different in the Mac world. So Windows and Linux might also be a limitation here. So what are alternatives that you could use? The most popular alternative in comparison to CUDA is probably OpenCL. It is cross-platform and cross-vendor, which means it can run on any GPU and on any platform, or at most of all at least. Like the organization behind OpenCL, it's the same organization behind Vulkan, Kronos, and they're gonna take care that everything is like supported. They do define standards, they have a quite big influence, and if there would be any new systems popping up on the system or operating systems and stuff, then probably they're gonna actually adopt the standards of OpenCL, and so it's basically available everywhere, with asterisks. Two other alternatives are seen in modern rendering frameworks. So Vulkan and DirectX provide compute shaders, so basically a very simple way, and just a single shader, a very simple pipeline state. So very simple states that you can put into these rendering APIs to run compute applications. So for example, DirectX is cross-vendor, but it is Windows only. So if you're writing a game which runs only on Windows and Xbox, for example, then you could easily use DirectX compute shaders and you don't care about the hardware. It's gonna accelerate your stuff on the Xbox, where you have an AMD GPU, and it also runs on any desktop system with Intel, Nvidia, AMD CPUs. On the other hand, we have Vulkan, of course, which is cross-platform and cross-vendor, but also quite complicated and not as easy to debug and stuff, while still possible. But Vulkan is like the hardest rendering API to get into. I think from my point of view, DirectX 12 is easier than Vulkan. OpenCL is kind of like in between. I'm a DirectX guy, so I know DirectX, but probably OpenCL is a bit easier than DirectX anyways, but not as easy as OpenCL. So this is why I am kind of like now coming to the last point. Why do we use CUDA? Well, because it's easy to learn. We have amazing debugging tools, we have amazing integration, we have a simple API, we have a simple SDK installer, we don't need to clone a GitHub repository, install all dependencies, build everything, export the data. Basically, if you go to OpenCL and click at SDK, you are redirected to a GitHub repository where you can download the source code, and yeah. It's a bit harder to install, like we like installers, we want to have it simple and stupid. Alright. And also another thing, later it's not very hard to switch to the other API. The concepts are the same, only the API is changing. Of course, if you are using like DirectX compute shaders, you need to adopt your code to run that HLSL. So you basically all HLSL functions, but probably porting isn't that hard because it's quite similar. You will have a sine function, you will have a cosine function and stuff. So you just need to kind of like adopt the HLSL syntax there. Same here with Vulkan. Vulkan is now also compatible with HLSL, so this means that you can write this in HLSL and then spear vdes cross-compile to Vulkan and stuff. And also OpenCL. OpenCL is also quite similar to the CUDA syntax. It's just the API that is kind of like changing, and you need to change minor things, but your algorithm or all the concepts you're gonna learn in the series is gonna adapt and apply to everything else as well. Alright, so now let's start by downloading the CUDA toolkit. Can I? No, I can't. I need to get out of this. So let's open up this URL and let's grab the CUDA toolkit. So here we are at developer.nvidia.com/CUDA toolkit. It has a nice video that's introducing you the latest features of CUDA 11 that we're gonna use. So yeah, like Is there anything that we can show that's looking nice? Yeah, basically you can see a bit how this works. So basically down here, here's a development environment. You have here like your desktops, your data center, custom solutions, supercomputers, GPU accelerated cloud. This kind of like the Nvidia hardware that you install on your system. On top of this is the CUDA API, which basically builds on top of the Nvidia hardware, interfaces the Nvidia hardware, and basically make sure that it's being run on your hardware. And then above CUDA, you have CUDA X, which are libraries that can help you getting started. So it supplies ready-to-use algorithms that you can use, and on top of that you can build your AI, HPC or graphics application, whatever you want. High-performance computing is like for example, geometry processing would be counting to high-performance computing, graphics, image manipulation would count to graphics, culling would count to graphics, and AI is basically artificial intelligence. I'm not an AI expert, even though I might want to look at this, but I have not that much time to learn everything, so AI is something that I'm not familiar with at all. So I can't tell you anything about that, but yeah. And also, it's providing you amazing debugging tools. So the Inside System Profiler can easily show you what's going on. So it shows you your CPU timings, your CUDA timings down here. Basically, everything is integrated into amazing debugging tools, visual debugging tools, where you can easily like do stuff. Yeah, you can find several information about CUDA down here, but we actually just care about this download now button, which is gonna bring us to CUDA 11.6 download, and we want to go for Windows, and you now have an option to select something. We want to select that, and we're actually on Windows 11, so I'm selecting Windows 11, and you basically also want to just select the version that you have. I don't care which version you have, it's gonna work the same in the SDK. We're just gonna select the exe file, and yeah, there we go, we get something, and we get a download which is 2.39 gigabytes big. So yeah, we're gonna see as if the download finished. And I actually gonna open this up. I'm not gonna show you how you open up an exe, but most of the time installers do take time. So yeah. Right, here we are in the Nvidia CUDA installer, which is like amazing like any other Nvidia installer. It's checking for system compatibility first, which is also taking some time, and I probably see like this installation is taking time, but yeah, there we are. So what you're gonna do is you're gonna read all of this text here, and if you agree with that, you can agree and continue. Then it's gonna ask you how you wanna install this. I wanna go to a custom to basically select what I wanna do. So first of all, CUDA, you can see that there are several things. It's also installing NVIDIA's development tools, the Visual Studio integration, the sample, the toolkit, the documentations, runtime, of course, development, things like compiler, tools, libraries, all that stuff. By default, it should be all selected and good. What it's also installing is, it is installing GeForce Experience. Yeah, why not? Current version. Actually, I have a later version that is more modern, so I can actually unselect this. What it's gonna do with physics, it's gonna install the same version again, so I'm probably not gonna need this as well. Well, I could just, yeah, we're just gonna leave this checked. It's probably gonna see, alright, it has already installed this. Display driver, this is something that I always like. It's actually installing a completely new and different driver. Right, so I'm just not up to date, so everything is good. So are we actually on 5 now? That is good to know. But yeah, basically it's gonna also update my drivers. So now I want to installer. So I'm actually fine with that, leaving the driver in here. I have a more modern version of GeForce Experience, so I'm not gonna select that one. So just to make sure that everything is correct. Right, the next thing that we're gonna get is this installation location folder. You can actually adjust these, but it's a pain in the butt since the select here is not quite good, and you cannot like just say, alright, install to different drive. So also for simplicity that it's the same like on you, I'm just gonna leave this at the default. So I'm gonna click next, and then I'm gonna go to install, and now it's gonna install this and probably gonna crash my recording because, yeah, it's installing a new graphics card driver, so I'm gonna pause and stop the recording for this installation here. Alright, so after a system restart, the installation is completed. And now we can start and create our first project. For that we're gonna need Visual Studio 2019 because 2022 is not supported yet. Or at least it hasn't installed all integrations, so I'm gonna use 2019 and I'm gonna create a new project, and the project will be of type after Visual Studio has loaded 16,000 hours. What is that? Ah, that's some inside stuff. After clicking a new project, I'm gonna create a blank solution here. And this is, wait a minute, you probably have my path right. Yes, GitHub projects. And this is basically my CUDA tutorial. There we go. Created. Solution name CUDA tutorial. And what? Nope, I want to go to Solution Explorer and Visual Assist. Yes, I have installed this thing now. And what we're gonna do is we're gonna create a new project in here, and we should have like all platforms. Is there CUDA somewhere? CUDA, I'm looking for CUDA. Data science. Yeah, CUDA. There we have it. Is it really data science? Or let's actually try this out. I'm gonna select all, and I'm just gonna hit, or is there actually a language called CUDA? Yeah, there's a language called CUDA, and this is the right project. Machine Learning, Desktop Data Science Console, Cloud, Linux, Windows, CUDA, C++. Yeah, that's what we want to do. Alright, so we're gonna create a CUDA one in here, and that's gonna be called 01. Simple vector add. So we're gonna add some vector. Simple vector add. Create. Alright, and this should create us a default CUDA project, and this is where we're gonna start everything, because it's already that is already our ad application. I know it is a default CUDA thing. We need to delete this. Do I want to delete everything? Probably yes. And at least like not the main. We're gonna delete like everything instead of the includes, of course. So let's get rid of all of that. We don't need this. And let's write our own int main and stuff, and just click on run to see if it's working. It should at least open up. Yeah, like that, and does nothing. That's exactly what we want. That's good. But it probably has shitted out our full directory that we have just created. So let's do a sample project cleanup. Put this all into a binary directory. Let's go to all configurations and everything, and let's simply just change the output directory, and so like that, and then we're gonna have a slash, and that's it. And then our output intermediates, same directory but obj, subdirectory. So project name configurations, and we should be good. Then we're gonna go to do debugging, and we want to select the working directory to be the solution directory. Does that work? Yeah, it works. All right. And then we have some CUDA options here, but for now, yeah. So this should conclude our project setup, and now we have a bit more clean setup here, and we are now ready to start writing the code that we're gonna need for the tutorial, but we're gonna do this in the next video. Thank you for watching. See ya. Bye.